Okay, what I'm going to do today is first of all make a couple of announcements. So this should be passed on to everybody else. There's a slight change in the schedule. I said originally there would be no meeting on the Friday after the spring break in the original schedule, but we will meet then. I'll fly back from Los Angeles faster. I was just saying that there was a slight change in the schedule, which is in the initial sheet. I think I said on the 20th we would not have class, which is the first Friday after the spring break. But it turns out we will have class because I've gotten a faster flight back from Los Angeles. So the rest of the schedule may change after that, but we haven't done it yet. And this is the attendance for today. And some additional homework. So why don't you distribute the additional homework? Okay, thanks. Okay, what I wanted to do today is discuss perhaps one of the most used methods of analysis in psychology, which is analysis of variance. But what I wanted to do is to lead up into it to describe the context in which it's used and how people go about interpreting some of the results. So what we're going to do, if you could switch to the Elmo. Thanks. This is usually abbreviated as ANOVA, which means analysis of variance. And as I may have told some of you, I don't like this. So I'll explain my biases and why I don't like it and why a bunch of other people like it. So I'll give at least a balanced but negative interpretation of this. Let me start one step back from this. One step that's more, more basic. And this is homework. Thank you, or you're welcome. Let me go one step back to discuss what the basic paradigm is that's normally assumed in lots of psychology. Remember, paradigm is a way of looking or a way of thinking about a problem. The basic paradigm, I think, has two aspects to it. The first is correlational. That is, we have some sort of independent variable that we vary. And we see the response of the dependent variable. So we measure the response of that. And then what we do is we correlate, we compare the response of one to the other. So for example, we can vary the alcohol levels and look at the effects on motor performance, for example, in a task. So in that case, the independent variable would be the alcohol, and the dependent variable would be the motor performance. Now, this seems sort of obvious, and most of the textbooks in psychology just sort of go ahead and develop this paradigm without discussing what the implications of this are. There's also an implicit assumption in here that in some deep sense, this correlation is what I will call linear. And if it's not linear, and we'll see by the examples I give today what linear means, that something screwy is going on. The problem I have with this paradigm is that the world is not linear, and very often nothing screwy is going on. That's the way of the world. So linear kind of means, and we'll see this in more detail, if I have the dependent variable here and the independent variable there. I usually say the wrong words for this. I felt lucky today after I got it right the first time. I thought I was going to go through the whole thing without not making one mistake like this, but I'd made at least one mistake. The assumption is that we can draw a graph that looks like a straight line, which is why this is called linear. And if we see something that looks like this, then we get all upset about it. On the other hand, things like this are very, very common in life. If you eat a little bit of sugar, it's probably good for you. But if you live by eating entirely sugar, it's probably bad for you. And so this idea that there's a monotonic, that means in the same direction, and a linear dependence of one variable on the other is actually counter to most of our experience with real living things. And so we'll see, though, how this usual paradigm, when things are not linear, interprets them as being screwy. But they're not screwy. That's very much the nature of biological and, in general, physical nonlinear systems. So let's see this by a number of examples. And what I'm going to do is give you examples of an experiment where we measure something. So we're measuring something. We're measuring this dependent variable as a function of the independent variable. And this is a trick so I don't have to write as many things and I can talk faster and make it more difficult for you. Because remember, I try to write things down to slow me down. So this means I've avoided the trick. So for example, what we might be measuring as the dependent variable, as I said, is motor ability. In the old days, this used to be done by having a turntable that played records, and there would be a hole in it. And you'd have a little wire, and you'd have to follow the little hole as it turned around the turntable. And if you missed, it would hit the edge of the hole and record an electrical signal. But we don't have records anymore. So I don't know if they have these machines anymore. Although I have a machine at home that plays records. But it's very dusty. So the independent variables that we might measure here, we might give people alcohol, or we might give people Tylenol, and see how that affects their motor skill. So we have two different independent variables, which from now on I'll call A and T. When I first wrote this up for a class a couple of years ago, I gave them alcohol and aspirin, and it was an A and A, and that was not good. So we switched to Tylenol the year after. But that also shows the importance of notation. And I also think that's why independent and dependent variables are not good names for things, because they're too easy to confuse. Notation is very important. Later on today, if I haven't told it already, so like the Thamidorian skipping suddenly into the future, and then I'll skip back into the present for a second. What I'm going to say later is that we're going to have three sets of equations with variables like x, y, and z. And I had a problem when I was in my first year calculus course in college, where we had three equations and three unknowns. But there were these Greek letters. And this one's not drawn well. And no one in the class solved this problem correctly because no one could write the Greek letters. The only person in the class, although the mathematics was simple, everyone could do the mathematics, the notation was too confusing. And the only person in the class who got the problem right was a guy named Alan Namath, who said let at the beginning, this equals x, and this equals y, and this equals z. And this seems like a trivial thing, But how we choose notation and how we set up problems is very important in how we think about them and how we manipulate the symbols. And this was a very clever thing for Alan to do. And we'll see this in terms of how we write the between and within variances in terms of the ANOVA in a few minutes. But now skipping back into the present. So what we have, and I'll draw a table of data, and there's another point here too. I tell this to my undergraduate class. I don't think anyone ever does it, but you people have more experience, which probably means more failures in thinking about things, so you may be willing to try this more, is if you're not sure about something, for example, a statistical test, you can always put trial numbers into it. Put numbers that you make up and see what happens. And that will help you understand the statistical test. For example, if we have an experiment and a control, and the values are 3, 2, 1, 1, 3, 1, if I wanted to understand how a t-test worked, I could do a t-test and make up this set of numbers, and then do a t-test and make up a different set of numbers, like the experiment could be 100, 200, 183, and the control could be 1, 3, and 1. And then if I do a t-test on these numbers I make up, I can see what the p-values are and how things work. And this will help me to understand the test. If I get a p-value of like this for here and this for here, then I know that this is not what I want if the numbers are different, and this is what I want if the numbers are different. So if you don't understand how a statistical test works, you kind of know what the test is trying to do. It's trying to tell a difference between two things, and so you can give numbers that are the same or the different and just see how the test works and see how the parameters of the test are computed. And this is a very useful strategy to help understand some of these statistical tests. So today what I'm going to do is give you a set of numbers to help you understand main effects and interactions. And the numbers I'm going to start with are, we're going to look at the effects of 2 levels of Tylenol, which we'll call 0 and 1, and 2 levels of aspirin, which we'll also call 0 and 1. And these numbers I'm going to put in the box are the values of the thresholds of the motor skills that we find. So in this case, the numbers will be 10, 15, 20, and 25. And maybe I'll even make them big enough so you can see them well. And we're in nice sharp focus today. So far we have good focus and only one so far independent variable mistake. Okay. And what I'd like to do is to draw graphs of these numbers. So this is another general rule. So the first rule we have today, if you want to help understand things, you can make up numbers and try them. Another useful principle from today is numbers are hard to understand, so we can turn the numbers into pictures. This was a technique that was pioneered by René Descartes. Descartes. And I mentioned once before there's some awful pun that ends in putting Descartes before the horse, but I don't remember how it starts, so I can't do it. And he wrote under the name Cartesius, which is where we get the name Cartesian coordinates. This was at a time where people wrote in Latin under their Latin names. But this was basically a technique that he and his followers pioneered, is turning, in their case, really equations into graphs, and then studying the properties of the graphs. And this was a very clever idea. So very often graphs can help us see things that we can't see in the numbers. And this is part of this usual principle that I've been explaining a number of times, that faced with a hard problem, what we should do is not solve the hard problem, because that's hard, but translate it into an easy problem and deal with the easier problem, in this case in terms of the representations. And we can see that we can see things in the graphs that we can't see so well in the raw numbers. So let me plot the graphs. And I'm going to actually make real graphs, try to really make the axes quantitatively accurate and everything. So let's see if I can do it. So this is going to be 5, 10, 15, 20, 25, 30, 35. And over here it's going to be 0 and 1. And what I'm going to do here is plot the thresholds versus the level of alcohol. And on another plot, I'm going to plot the levels of Tylenol, how the thresholds depend on the levels of Tylenol. So this is the same axis here. And let me now plot this data. The reason why I'm doing this is two-dimensional data, so I should really plot it in 3 dimensions, but it's hard for me to do that, so I'm going to make two-dimensional plots. So when the level of alcohol is 0 over here, and the level of Tylenol is 0, we have 10 for the threshold. And when the level of alcohol is 1, and the level and the level of Tylenol is 0, we have 20. So I'll plot this up here, and I'll connect these by a line because this line represents the same levels of Tylenol for 2 different levels of alcohol. So this line is the level of Tylenol equal to 0. And this is alcohol 0 and alcohol 1. And now I'll plot the level for Tylenol equal 1, which is down here. For alcohol 0, it's 15, and for alcohol 1, it's 25. So this is 15 and 25. And this is for Tylenol 1. Now, this plot contains all the data, because I've got 4 pieces of data, and 1, 2, 3, 4 pieces of data. See, counting to 4 is easy. So this contains all the data. But sometimes we like to represent this. Maybe we'd like not to have the alcohol presented this way in the Tylenol, but we can do the mirror image of that, the reverse, where I've plotted the Tylenol level. So let me do that. And the Tylenol level goes for 0 to 1. At 1 level at 0 alcohol, this goes from 10 to 15. So this is now at the alcohol level of 0. And at the alcohol level of 1, the results go from 20 to 25 as we go from 0 to 1 in the Tylenol. So that's 20 to 25. So this is alcohol level of 1. So this contains all the data presented in plots in 2 different ways. Now you see that the slopes here are different, so that the slopes here, these are steeper than that. These are shallower. So we're presenting the data in 2 different ways, but we can view them in both of these ways. Okay. So now let's look at how this threshold value, these numbers in those boxes, change as the alcohol level, at the alcohol level of 0, as the Tylenol level changes. We just want to do the opposite. What I want to look at is as the Tylenol changes for a constant level of alcohol equal to 0. But what we've seen here is at this level of alcohol equal to 0, the Tylenol, so let's look up here again. At the alcohol level of 0, which is across here, as the Tylenol changes, the threshold goes from 10 to 15. So that's a change of +5. And at the alcohol level of 1, it goes from 20 to 25, which is also a change of +5. Okay? So what we see here is that as Tylenol changes from 0 to 1, the change in the threshold is +5 regardless of the level of alcohol. Okay? And we can do the same thing to see what happens as the level of alcohol changes. So now as the level of alcohol changes at a constant level of Tylenol 0, going back to looking at my plot, which you can't see, but maybe we'll put up here. So at the alcohol changes from 0 to 1 at a now we want to go this way. So the Tylenol level at 0, we change from 10 to 20. So we have a change of +10. And at a Tylenol level of 1, the change is from 15 to 25. So we have a change of +10. So again, we have a change of plus 10 when the alcohol changes, regardless of the level of Tylenol. Now you can see that for the two different variables, the changes are different. This one is plus 5 and this one is plus 10. But the point is that the changes in one do not affect, the level of one does not affect the changes in the other variable. Okay. And this plus 5 is reflected, the fact that these are plus 5 is reflected in the fact that these curves are parallel. And the difference between the plus 5 and plus 10 is the difference in the slopes between these two. So these are both parallel, which means we get a similar change in the threshold when we change the alcohol. This change is the same as that change, even though there are different levels of Tylenol. And this change is the same as that change, even though there are different levels of alcohol. The amount of change here is different than the change there, so the effect of Tylenol is different than the effect of alcohol. But the level of alcohol does not affect the Tylenol, and the level of Tylenol does not affect the level of alcohol. Okay. And the jargon words we use to describe this are that we say there is a main effect of alcohol that is on what we're measuring, which is the threshold. And we also say there is a main effect of Tylenol. So the crucial thing is this main effect word. And we can also say that the main effect of alcohol does not depend on the level of Tylenol. And similarly, the main effect of Tylenol does not depend on the level of alcohol. I'm beating this to death because we're going to see in the next two examples how these things change for the different examples. But I'm trying to set this up. And that's why these lines are parallel. Okay, are there any questions on this so far? Okay. How many people here are used to hearing words like main effect? Okay. So then it's good we're saying the words. If you knew all the words, then I wouldn't have to say anything, right? And you'd have to sit here for 3 hours. So now let's example number 2. Not 12, but 2. Now the numbers are going to look like this. 10, 20, 15, 35. So I'll zoom in so you can see what the little box looks like. And we're going to make the same graph again. I'm going to zoom out. Same sets of 2 graphs. So this is going to be 0 and 1 for alcohol, 0 and 1 for Tylenol, 5, 10, 15, 20, 25, 30, 35, 5, 10, 15, 20, 25, 30, 35. Okay, so at alcohol 0 to 1, at level of Tylenol 0, we go from 10 to 20. This is at Tylenol 0. And at Tylenol 1, we go from 15 to 35. And here, at Tylenol 0 to 1, at alcohol level, we go from 10 to 15. And then we go from 20 to 35. Okay? So let's do the same changes business we did before. As Tylenol changes from 0 to 1, at alcohol level of 0, we change from 10 to 15, which is a change of plus 5. And at alcohol level of 1, the change is from 20 to 35, which is a change of plus 15, which is not the same thing as 5. Okay? And as the alcohol level changes from 0 to 1, at Tylenol of 0, we go from 10 to 20, which is a change of plus 10. And at Tylenol level of 1, we go from 15 to 35, which is a change of plus 20. Okay? See, I can do this faster and faster when I get a little practice in what I'm doing. So now what do we have here? What do we say we have here? Well, we still have a main effect of Tylenol because when we vary the Tylenol, we vary a change in threshold. And we also similarly have a main effect of alcohol. But you can see now that these lines are not parallel. Lines are not parallel, meaning that the effect of alcohol depends on the level, the effect of Tylenol depends on the level of alcohol. And similarly, the effect of alcohol depends on the level of Tylenol. Okay? And what we call that is an interaction. So we say we have an interaction between the alcohol and the Tylenol on the threshold. And again, to show you what highlights the interaction is the interaction shows up in the fact, 1, that the lines on these plots are not parallel. And 2, that means that the changes in one variable, one independent variable, depend on the level of the other independent variable. Okay, so that's what we mean by an interaction. Another way to see this is to say that if there was no interaction, then these lines would be parallel. And so if there was no interaction, we would get this, and we have an added effect. And we can see that here too. So taking the alcohol and taking the Tylenol are not additive. The effect of taking both is more than the sum of the two. So that's another way to say that the interaction, that the effect of both is more than the sum, that means we add, of both. One way to say this is that it's synergistic, which just means this. Okay. Now, to me, this is a stupid way of looking at it. And first of all, this happens in many cases. For example, if you smoke cigarettes, I think you have about a 5-time chance of increasing your rate of cancer. And if you are exposed to asbestos, you may have a 5 times rate of getting cancer. So this is just smoking alone and this is asbestos. I don't remember exactly what the numbers are, but there's something like this. So you would think if you do both, you might have a 10-time chance of getting cancer. But in fact, if you do both, your chance of getting cancer about 25 times. So it's not, doesn't add up. It's much more dangerous to do two things. And this is actually true for a number of carcinogens, actually. If you smoke and you're exposed to the carcinogen, then your chance of getting cancer is synergistically increased. So this is actually common in some things. Now, the reason why I think this is sort of silly is this is based on the assumption that things are linear. That is, that we expect when we have something 5 times and 5 times, we add them. That's what linear means, that things are additive. Additive. And let me now show you this in a more direct way. I can't do this for my undergraduate class because they don't know about partial derivatives. But some of you know about partial derivatives, so I can say it this way. Let's say I call the thresholds I've been using here R, because I've used T for something else. What this linear model is basically saying is that R equals some constant, which maybe I'll call little t, times the Tylenol, plus some constant, which I'll call little a, times the alcohol, where these little a's and t's are constant. That's sort of the assumption. Why is that assumption? Well, let's compute now the slopes that we would get from taking the partial of R with respect to Tylenol, which is what the slope on that plot is. Well, that's equal to t, which is a constant. And the slope with respect to the alcohol will be this little a, which is a constant. And so we'll wind up with these parallel lines. They'll have a different slope in each case, but they'll be parallel. And that's what we think is kind of what we're looking for. And if we don't get this, then we say there is an interaction. So if not, then we say there is an interaction. But there's no reason why the world is linear. An example might be a nonlinear, something nonlinear. So let's say the correct relationship is that R equals little t times little a times t times a. Now let's see what the slopes look like. The R dt now is t times a times a. So the slope depends on the level of alcohol. And that's what we're calling an interaction. Or if we look at the other slope, now we see that that slope of the alcohol depends on the level of Tylenol. So there are two ways of looking at the failure to have the slopes. The standard psychological interpretation is to say there's an interaction between the two variables. But to me, all that's saying is really the function of the variables is nonlinear. That the effects of the two variables don't add. Now, to me, this is a more reasonable interpretation than hoping that everything is linear, and if it's not linear, calling it interaction. It's not intrinsically different because you're seeing these two things are really related, but it's kind of where our starting point is. We have no reason to believe that the world is always linear. When we vary things a little bit, typically the world is linear. When we vary things a lot, it's not. And I think a lot of this stuff of thinking of the interaction is kind of misleading, because what we really have is a nonlinear function of the variables, and there's nothing that should be surprising about. Okay? Now, let me give you the last example of this sort of business. But we need this concept of main effect and interaction in order to handle the ANOVA, which is why I'm running through this now. And also because this was in my notes, I think it's worthwhile to cover, because although you should have had this in psychology undergraduate, even last time I taught this course, not everybody had this, so I thought it's worth going through. And it was out of order in my notes, so I couldn't remember what lecture it belonged into, and this seemed like a good lecture for it to belong if we needed to understand the ANOVA. So that's what happened. There are sets of 3 and 4 notes that are mystically moving by their own motive power through my notes. You leave them in the drawer, and they just manage to translocate themselves, teleport themselves. So this is example number 3. And remember, we're still only one failure on the independent-dependent variable business, so we're still doing very well on that. And now let me show you the numbers I've made up here. The numbers here are 10, 15, 20, and 0. And I'm now going to draw the same plots that we've drawn before. So this will be levels of alcohol at 0 and 1, and levels of Tylenol at 0 and 1. And it's going to be 5, 10, 15, 20, 5, 10, 15, 20. So when the level of alcohol goes from 0 to 1, at Tylenol 0, this goes from 10 to 20. So this is Tylenol 0. And at Tylenol 1, it goes from 15 to 0. 15 to 0. So this is Tylenol 1. And this is at Tylenol 0 to 1, Tylenol 0 to 1. At alcohol 0, it goes from 10 to 15. 10 to 15. This is alcohol 0. In alcohol 1, it goes from 20 to 0. 20 to 0. And this is alcohol 1. Okay. So let's look over the same business we've done before. So as Tylenol changes from 0 to 1, at level of alcohol 0, Tylenol changes from 0 to an alcohol level, we go from 10 to 15, which is a change of plus 5. At alcohol level of 0 at 1, we go from 20 to 0, we go to minus 20. Doesn't even go up, it goes down. And as the alcohol level goes from 0 to 1 at Tylenol of 1, so alcohol goes from 0 to 1, Tylenol, let's say Tylenol of 0, we go from 10 to 20, which is a change of plus 10. And at Tylenol level of 1, we go from, alcohol goes from 0, we go from 15 to 0, which is a change of minus 15. So you can see now here we have a very strong dependence. That is, the changes in Tylenol depend very strongly on the alcohol level. And similarly, changes in the alcohol level depend very strongly on changes in the Tylenol level. In fact, in this case, they depend so strongly that you can see in this case they actually the interactions cross over each other. Not only are these lines not parallel, but they cross over each other. And so therefore this is called a crossover interaction. What all this is really saying is that we have something nonlinear. That in one case, if we give a change in Tylenol, at one level of alcohol things go up, at the other level things go down. But again, that shouldn't be so surprising. If you have a little bit of sugar in you and take some alcohol, it doesn't have any effect. But if you have a huge amount of sugar in you and you take the alcohol, maybe you'll get sick and you'll have the opposite effect. So all this is really saying is that we have a strong nonlinear interaction. But again, this predominant paradigm of thinking of things should be linear first, and then if they're not linear, we say, oops, there's an interaction, is kind of the underlying way that at least the psychology people interpret this. But again, the deeper aspect of this is that we're still assuming that what we want to do is to correlate one thing with another thing, with the dependent variable and the independent variable. And that's also a hidden assumption built into this. Okay. Well, now, based on this, are there any questions on these three things? So we first of all had no interactions, a interaction, and a crossover interaction. Those are the three things we've done. So maybe I'll write that down. These three examples represent, and each of them, at least in the first two, there's certainly clear main effects. And then we've seen we had an interaction, so this is a main effect. And we first of all had examples of no interactions, and now examples of an interaction, and then examples of a crossover interaction. To symbolically represent things, which means basically drawing plots without labeling axes, so it's harder to tell what they are. Okay. Are there any questions on this? Let me ask again for questions. So this is okay. This is, again, the usual psychological jargon for handling this sort of experimental data. So it's good that everybody should know. And you'll hear these words. I think even in the journal club and in the research meetings, I've heard the words, if not this year, at least last semester, people say the words main effect and interactions. So, I mean, I've heard those words because I listened for those words. But I listen for other words as well, too. Okay. So now what I'm going to talk about today is, as I said, analysis of variance. Okay. And this is based on a statistical test, which is called an F-test, which is named after a person, R.A. Fisher. I think it's Richard. Is it Richard? No one knows what Fisher's first name is? It's not Richard? Fisher was a part of a group of social psychologists that developed a lot of statistics soon after the turn of the century, maybe 1910s, 1920s, roughly, I think. Is that about right? A little later? So, but something roughly in there. At least that's the right century. Basically, the test asks the following question. Let's say we have two sets of data. We have data set number 1 and data set number 2. Okay, so we have two sets of data. And the question we want to ask is, do both these data sets have the same variance? Okay. And that is the same spread. So if I plot these in the usual way of number versus value, for data set 1 and data set 2, there'll be some error. They're not exactly Gaussian, so we want to know if the spread of this one is statistically significantly different from the spread of that. So that's what we're trying to find out. And what he developed a statistic to do this is the F statistic, which is equal to the standard deviation measured from the data times n1, the number of data values in the first data set divided by n1 minus 1, divided by 1 over sigma 1 squared if we know the true variance in the first data set, divided by similar factor for the second data set. And this is called the F statistic. And the number of degrees of freedom, it comes with number of degrees of freedom. the number of data values in the first data set minus 1, and the number of values in the second data set minus 1. So when we look up for f, we have to look up for 2 degrees of freedom. And it's usually set up. We can set either in the numerator or denominator. It's usually set up so we make f greater than 0. So for example, in one of the problems, let's see if this is a homework problem. I don't think it is. In your book, problem 1118, for example, we're given the case where we have 9 measurements in the first group where we know that the variance should be 16, and S1 squared actually measured from the data is 20. And in the second group, we had 12 subjects. We know that the variance we expect is 25. The measured is 8. And we go through this, and we find that f is 4.028. If I use this formula. In my notes, I have written down the calculation, but the arithmetic is not particularly interesting. The number of degrees of freedom is 9 minus 1, which is 8. The second degree of freedom is 25 minus 1 is 12 minus 1 is 11. And it turns out that at the 0.05 level, f would be 2.95. And at the 0.01 level, f would be 4.74 from the tables in the back of your book. And since here we have f equals 4.028, then it's statistically significant at the 0.05 level, but not at the 0.01 level. Okay. So this is sort of the usual example of a statistical test. Now, this is a little bit odd statistic in a way, and we use it to compare data in sort of an odd way, because most of the time what we're interested in is not variance, but measures of central tendency. That is, we have an experiment and a control, and we want to find out whether the average or the mean or something of the experiment is the same or different than the control. You know, and that's not how we're going to use analysis of variance. In analysis of variance, we're looking at the variance, not the mean. And let me first of all start you off with an example of how we're going to kind of use this, and then I'll go into the equations and make it more specific. Let's say the numbers from the experiment are something like 10, 12, 13, 10. And the numbers in the control are 9, 11, 14, 10. Well, again, based on sort of comparing means or averages or something, the usual way of evaluating this would be to say, so what would seem to be a more usual way is we would say, for example, we would ask whether the mean of the experiment is really the same as the mean of the control. Right, that would seem like a reasonable question. Is sort of the value here the same as there? But that's not what we ask in analysis of variance. Analysis of variance is different. What we're going to ask is, and I can show it by giving a second example. So let me give a second example against the control. Now let me give 2 other examples, actually. I certainly don't like this example. Experiment control, experiment control. And maybe I'll do it this way. We'll stick with this first example, which was 10, 12, 13, 10, and 9, 11, 14, 10. Let's say this one, in this data set, it's 10.1, 10.1, 10.2, 10.1. and the control is 9.1, 9, 9.1, 9.0. Kind of our intuitive idea is that here we can tell if anything is going on. This looks not different between the experiment and control, but this one does look different. Why does this one look different? What we basically can do is we can compare the variation of the numbers within each group versus that between the groups. Now, we're not comparing means, really. We're comparing the variation. Here, the variation within each group is very small. And the variation within is less than the variation between, and so we think there's a real effect. So again, in this example, the variation within each group is small, and the variation between the experiment and control is larger. And when we have this, we'll say that we have a real effect. Sorry. On the other hand, in the first case, what we have is that the variation within each group is about the same as the variation between. So in that case, we can't establish an effect. Let me pull back again so you can see this. So again, here, the variation within these numbers, within the group, is about the same as the variation between, and so we can't establish an effect. Whereas here, the variation in each of these groups is much smaller than the variation between the groups, and therefore it seems like there's a real effect here. And so that's what the ANOVA depends on. In the ANOVA, we look at basically F ratios that represent variation between groups divided by the variation within a group. And if this number is large, then we say we have a real effect, and the probability that it's due to chance will be small. So if we have a big F ratio, the probability it's due to chance is small, and therefore we have a real effect. And this is the main principle behind the ANOVA based on the F test. Is this clear? Is it clear what we're doing here? Sometimes I do this better than other times. So I should have a set of numbers I pick in advance. Every time I do this, I pick different numbers each time. So maybe I should have a set of numbers that I picked once when it was a nice calm day and it wasn't raining, and I didn't answer the telephone when it rang, and I sat and thought and picked good numbers, and then I would just have one set of numbers.
Are there days like that?
Sometimes they're not close together, but sometimes. Okay. Today is going to be a day like that. I decided to have a good day today. So it's not working out completely well so far, but it's, okay. So let me give an example of the first type of ANOVA, which we'll call a one-way ANOVA. Okay. And basically what we're going to have here, we're going to have values which we'll call x, j, k. And the j index will indicate the treatment group. And then the k will indicate, within the group, the value within a group. This will become clear when I give an example. So for example, a treatment level 1 and there's only one independent variable here. So for example, we have either alcohol 0 or alcohol 1, or alcohol level 2 or alcohol level 3. And then the values we get from the thresholds from the experiment would be, in this case, x11, x12, because the first index indicates the treatment. This is treatment number 1, 2, 3, 4. So this is x13. Maybe we'll make this readable. x14. And this is treatment 2, so this is x21, x22, x23, x24, treatment 3, 31, 32, 33, 34, 41, 42, 43, 44. So we have 16 values at 4 different treatment levels. If we had up to n values, then this would be up to 1n, and this would be here then up to 4n. Okay. Now, the basic idea here is mathematically, the system that we're treating is that we're saying that the xjkth value is equal to some mean value plus some random element that depends on j and k, where this random element has a mean of 0 and a variance of sigma squared. See, I made it complicated real fast. See how I did that? So this is sort of the statistical test we're testing. We're testing, in essence, the null hypothesis that we can represent as all the data being the same. So we're going to say that we're assuming all these values come from the same population, and then if they're different, it means that the effect of the alcohol is different. Okay? So this is really the statistical thing that we're going to treat. Now, let me at this point interject and say one of the reasons why I don't like the ANOVA. Nothing in this test is different if I had ordered the alcohol levels different. So this test doesn't check the fact that as I increase the alcohol levels, I get a consistent change. All it does is it checks that the treatments are different from each other. Now, again, after having given all this linear stuff, if I plotted the effects of the treatment of the dependent variable, it was close, but I got it right, against the independent, if I saw some consistent change, even if it was nonlinear, that would make me happy. In the ANOVA, we'll get a statistically significant effect as long as the treatments are different from each other, but they don't have to form any coherent function. Okay? And this is crucial about the ANOVA. And this is the reason I don't like it. Because as a physicist especially, I like to look for functional relationships and meanings in the dependent variable as a function of the independent variable. Here we're not doing that. We're just comparing one treatment against the other treatments. And the order and the level of the treatments does not come into play here. Okay, so that's a crucial thing to understand about the ANOVA. I mean, it's said in the equations, but it's usually not said as explicitly in this in terms of the words and how the books, even your textbook, describe it. So the ANOVA is only testing if the conditions are different from each other. It's not testing if the conditions are different in a coherent way. So let me write that down because I said it well. Let's see if I can write it down as well as I said it. The ANOVA is testing if the treatments at different levels of treatment are different. It's not testing if these differences vary in a coherent way, whatever that means, functionally important something. So this is the crucial point about the ANOVA. And as I say, this is the reason why I don't like the ANOVA. But I teach it to you because everybody else is into this, so I make you like everybody else. But I don't use these. So, okay. So let's say for the moment in doing this analysis, just to simplify things a little bit, let's say we have the same number as I gave you before of measurements for each treatment. And we don't have to do this. They could be, they could vary. Hey, could someone close the door because we're getting noise a little bit from the other studio? Thanks. And let's say now that n is going to be the number of measurements. That's what I had before. And we're going to have capital T as the number of treatments. The mean value in each treatment is, and I'm going to call this the mean value in treatment J. I'm going to put a dot here, meaning that we've averaged over that second index, is 1 over n times the sum of k equals 1 to n of x j k. Okay, does everyone see why that's the case? Because each treatment is j, and if we sum over the n values running this index from k equals 1 to n, then we have the value within each treatment. And this is called by a number of different names. It's called the group, and there are j's of these. So there are a total number of t of these, one for each treatment. These have different names. They're called the group means, because they're the means within a group. They're called the treatment means, because sometimes we call the groups treatments. And they're also sometimes called the row means. And the reason why they call the row means, if we go back to this, you can see that we're going, if the treatments are arranged in rows, then this is the mean of each row. So it's also called the row means. Okay. Now, overall, we can also formulate a different mean, which we will call the grand mean. Sounds like something from the Royals. The grand mean is the mean of everything. So what is the grand mean? And I'll represent 2 dots here because now we're averaging this over the treatments, so there's no index for the treatments. So this is the mean of the means. So this is the mean of the group means. So we take the group means and find the mean. So this is 1 over the total number of treatments times the total number of values summed over the total number of treatments. Let me write it in a different way. Let me write this as 1 over t times the sum over the groups, or the treatment means, j equals 1 to t, of the mean of each one. Well, we just said the mean of each one is 1 over n times the sum from k equals 1 to n of x j k. So I can write the grand mean as 1 over t to the n, t times n, times the sum from j equals 1 to t over the treatments, over the numbers within each treatment, over the values. Okay. Now, the basic idea here is, as I said, is to compare the within group variation against the between group variation. Okay? And now we're going to see how we go about doing that. We'll see how far we get before we break. First of all, let's look at what I'll call the total variation. So what does that mean? Total variation, which we'll call V, is going to be the difference between each value and this average over here. I left out the bar on. So the total variation is each measurement minus the grand mean. And that seems like a total variation, right? So each one minus the mean of everything. So we need to sum these first over treatments. So this is the first sum is the sum over treatments. And we need to sum over groups. over the numbers within each group. So in essence, we're summing over the between, and we're summing over the within. So we're including everything. So then the index here is within is k equals 1 to n. Okay? And square this, because we're looking at the variation, the variance. Sorry about that. Okay. Does everyone have a sense why this is the total variation? Because we're doing all the numbers, in this case all 16 of them, minus the total average, and we're taking the square of that. So that's kind of like the total variance of everything. That's the total variation. Now we can define the variation within treatments. We're going to call this W. And this is going to look something like each one, each value, minus the mean within each value squared. Okay? So this is within a treatment. So if, again, these rows are the treatment and these are the values, we're going to look within within a treatment, and each case subtract this from the mean value within that treatment, this one within the mean value, that one, and square it. But in order to include, so for each treatment, we sum from k equals 1 to n. But we want this for all the treatments separately, so we also sum over the treatments. So this is the total variation within each treatment summed over all the treatments. Okay, and you see again what this is. Within a treatment, we take a value, subtract out just the mean. So each of these treatments has a mean. And we look at the difference of the value and the mean within that treatment, find the square of that, and then do that for all of the treatments. Now we have the last one, which will be the variation between treatments. Okay. And we're going to call this B. See, we've cleverly called this within, W for within, and B for between. The V is a notation the textbook uses, and we've used T too many times anyhow, so calling that the total variation is hard. So this between variation, what is this going to look like? This is going to look like we look at the mean of a treatment, and we look at the difference between the mean of a treatment and the grand mean. Okay, because that's what between is. So let me draw again. If we have this is the mean here, and this is the mean of that one, this is the mean of that one, what we're looking at across treatments is the difference of this one between everyone, and this one and everyone, and this one and everyone. Okay? So it's the mean within each treatment minus the grand mean squared. And again, we have to sum over treatments and sum over all the numbers. Well, when we sum over all the numbers, that doesn't affect this. That produces just an n. So this is equal to n times the sum over the treatments from 1 to t of x, the mean of each one, minus the grand mean squared. Okay? And it turns out, from these three definitions that I've given before, it turns out that the total variation equals the within treatment variation plus the between variation. This is important. And that comes out just from the derivation of the formulas. So the basic idea now is to compare to create an F-test where we compare the ratio of the between to within with the number of degrees of freedom equal to t minus 1, the total number of treatments minus 1, because that's the between. That's the number of things in the between, or the number of treatments minus 1. Within a treatment, the number of degrees of freedom will turn out to be t times n minus 1. And we compare this F ratio, and if this F ratio is much bigger than 1, then that means that the differences between are much greater than within. It means the p-value is small, and there are real differences between the treatments. Okay, we'll see how to plug these numbers into the statistical test after the break, but does everyone have a sense of where we are with this? There are a lot of pieces that I'm building up in here, and when we get to the two-way ANOVA, which obviously follows the one-way ANOVA, or I guess maybe the one-way bossa nova follows the one-way ANOVA, I don't know, whatever it is, then, because there are multiple paths, right, we can take on this thing. But what I'm trying to do is to build up the ideas of what we're using, and we're going to see now next, after the break, how to plug these into the formulas, and then we'll go up to the more complicated two-way test. So why don't we come back at 10:30? So we'll take a break until 10:30.